All right, this is lesson 10-5. We're going to be focusing on tangent lines tangent to a circle. So if you'll recall from the first lesson in chapter 10-1, we talked about some vocabulary. And we talked about the circumference of a circle is the distance around the circle. The center of the circle is how we name the circle. So it's a dot right in the middle, usually with a letter there like a P, and we would call that circle P, right? The radius of the circle, here I'll put a dot here. The radius of a circle measures from the center to the circle itself, that distance. The diameter goes all the way across the middle of the circle, so it's actually two radiuses, radii, right? The diameter. A diameter is a type of chord. A chord is a line that cuts across a circle, and its two endpoints lie on the circle. I know I'm not drawing this here because I don't want to focus on any of that. And then a secant line is a line coming out of nowhere, crosses through the circle, and keeps going. So the tangent line that we're talking about does not actually cross through the circle. It never enters our circle. It just brushes past the outside of our circle, right? And theoretically, if all it does is brush past the outside of our circle, it technically only touches our circle in one point. Now, I kind of drew my line too close. If you zoomed way in on this, my line kind of goes inside the circle a little bit. It's not supposed to. It's supposed to touch the outside. So when all it does is brush past the outside of the circle, it only touches the circle in one spot. That spot is called the point of tangency. Point of tangency. Okay, so there's a couple rules here. The first rule is the point of tangency between a line tangent to a circle is always perpendicular to the radius of the circle, right? So if I was going to draw a line between that tangent and the center of the circle right here, it's supposed to be 90 degrees. Now I'm hand drawing this, so it might not be exact, but it is 90 degrees, right? A line tangent to a circle is always perpendicular to the radius. Always. So that's the first rule that we have written here. A line tangent to a circle is tangent to a circle if and only if it's perpendicular to the radius at the point of tangency, right? And up here on this worksheet, they draw you a picture. So they drew the radius. They have this line which brushes past our circle. They stopped it right here, but technically a line's infinite, right? So it would keep going. It only touches our circle at point R. So this line, RS, is tangent to our circle, okay? And it's perpendicular to the radius here. If they're not perpendicular, if they gave you the measure of this angle between these two lines and it was 91 degrees or 89 degrees, it means it's really close to being perpendicular. So it might look like a tangent line, but if it's not exactly 90 degrees from the radius, then it's not tangent. It means it actually does cross through your circle somewhere, even if it's hard to tell. Has to be 90 degrees for this to be a tangent line. The second rule is if we drew some kind of point, not drew, but if we had some kind of point, let's say right here, outside the circle, right? The two lines that I could draw through a point of tangency in that point would both be congruent. What do I mean by that? If I drew, got my little Braden River business card here. If I drew a line tangent to my circle from this point, I can draw a line anywhere from that point, right? But I want it to be tangent to my circle. There's only one place where a tangent line touches a circle. I'm trying to get this as close as possible. So it'd be like right about here. And I wanted to also draw a line through this point tangent to my circle here. So it's going to touch my circle in one spot, hopefully. Right about here. Then these two lines from the shared point to the points of tangency are congruent, always. So when you have one point outside a circle and you draw two different tangent lines to the circle from that one point, those two lines are always congruent. Okay, so that's two rules. Tangent line, perpendicular to the radius. So if I drew the radius right here, there'd be a 90-degree angle here. If I drew the radius right here, there'd be a 90-degree angle here. Tangent lines are always perpendicular to the radius, and if we drew two tangent lines coming from the same point outside of a circle, those two lines are congruent from the point of tangency to the shared point, okay? Hopefully that makes sense. We're gonna do something else with that in just a second, but I wanted to go over a few examples here, so let's solve some problems. It says find x. Assume that segments that appear to be tangent are tangent. They're not always, right? In this case, they are. But once you get into a little more complex problems with circles, sometimes lines will look tangent, but like I said, they won't be tangent. They'll be super duper 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 close. They'll be like a degree off, but they won't actually be tangent. And you have to remember those rules of tangency, like a tangent line is perpendicular to the radius. So these lines are tangent, right? So since they're both coming from the same point C, and they are tangent lines, which means they touch our circle in one spot, that means they have to be congruent to each other. So to solve for x here, we would set x plus 3 equal to 7 and solve. I'm going to add x plus 3. I'm going to subtract 3 from both sides of my equation. X equals 4. And that's all we had to do was solve for x. Okay, so that's how you know how to do it. Let's do another one. In this problem, here is our tangent line JK. We know it is perpendicular to our radius JH here. And we're looking for this measurement, right? Well, what do I have here? A triangle. What kind of triangle? A right triangle, because these two lines are perpendicular. So I can use the Pythagorean theorem, right? A squared plus b squared equals c squared. 15 squared plus 20 squared equals x squared. 225 plus 400, that's 625 equals x squared. Square root, square root. The square root of 625, I believe, is 25. So here x would equal 25, and if you wanted to write it below that, x equals 25, that would be correct. Yeah. Number 3. Here we have, looks like an ice cream cone or a party hat, right? We've got one point here, point P, and we've got two tangent lines coming from point P. This tangent line touches my circle, it brushes past my circle, it touches it somewhere around here. And this line brushes past my circle and touches it somewhere around here. Okay, so that means these two lines have to be congruent since they came from the same point. So I could set them equal to each other, and x would equal 12. Done. Number 4. Here again, we've got the radius. This is a 90-degree angle when it's perpendicular to a tangent line. We want to find the length of just this right here now, okay? Just this portion. So how would we do that? Well, I know from R to U is 15, because that's the radius, right? From R to U. And this is 15, so this has to be 15. So whenever I find this entire side length, I'm just going to subtract 15. So to find the entire hypotenuse here, I'm going to use Pythagorean theorem again. So I'm going to call this whole side h, because it's the hypotenuse. So 15 squared plus 36 squared equals h squared. 225 plus, I don't know what 36 squared is, 1296. Is it really? Yep. Equals h squared. And add those together. 1521. Find the length of this side, which is h, so I got to take the square root. That's 39. So since the length of this entire side is 39, and we just want to know this portion, this plus this equals 39. So 39 minus this side is 14. So I'm going to do 39 minus 15 equals 14 over here on the side. X equals 14. Hopefully that makes sense. Number 5. Okay, we've got our radius here, the measure from the center to the circle, and then we've got this line that appears to be tangent, and it said in the directions, if it looks like it's tangent, then it is. So we know these are 90 degrees. We want to find the length of x, which is this guy right here, okay? So we've got our right triangle. I know this side. I'm looking for this side. Do I know the hypotenuse? I do. It's not labeled here, but the radius is 21. That means this part right here is 21. And the entire YB line is made up of YA plus AB. So 21 plus 8 equals 29. So the hypotenuse is 29. So 21 squared plus the other leg squared equals 29 squared. Oh, I'm gonna sneeze. 441 plus x squared equals 841. And minus 441 on both sides. X squared equals 400, square root. So x is going to equal 20. This length right here is going to equal 20. And lastly, number 6 here. We've got our radius, a tangent line, so we know they're perpendicular. We're looking for this entire hypotenuse. So we're going to use Pythagorean theorem. 17 squared plus 24 squared equals x squared. I have my calculator right here next to me so I can figure out radicals real quick, or exponents. 24 squared, 576. It's 865. And take the square root, and I get about, ooh, that's an ugly number, 29.4. Which makes sense. If this leg is 24 and the hypotenuse is the longest leg, it makes sense it'd be close, but 29. Let me just double check my math really quick. 289. Yep. 29.410888234, and I just rounded. Does it say to round? No, but I did. All right, questions, let me know on that. Let's finish this video out. I'm gonna go to the back side of my study guide here. Usually I do these in 2 separate videos. Right now I'm trying to rush through and just do one. Here, circumscribed polygons. So remember, we talked before about shapes being inscribed in a circle and then circles being circumscribed around the shape. So if I had a triangle that was inside the circle, all the vertices lie on the circle. This point, and this point are actually on my circle. So this triangle is inscribed, right? And then the circle is outside of the triangle. It's going around the triangle. It's circumscribed, right? So now we're going to talk about when the circle is inscribed and there's a shape outside of the circle. So the circle is going to become the smaller shape. Ignore these little points right here. And we're going to draw a shape outside the circle. Let's see, we want to draw, let's draw a triangle. Use my little quadrilateral. I don't know. We're just going to draw something. Boom. 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 So all of the sides of our shape are tangent to the circle, right? The circle is inscribed in this triangle. The triangle is circumscribed around the circle. So the outside shape is circumscribed, the inside shape is inscribed, right? That's what we're talking about. So for this lesson, we have circumscribed polygons, polygons that are going around a circle. So it says when a polygon is circumscribed around a circle, all of the sides of the polygon are tangent to the circle, what we just said with our triangle. They all touch our circle in one point, right? I can like literally draw those points on. Okay, for this one, it would touch here, 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 and here. All right, so we're gonna talk about a few things. Now, remember what we just learned in the last video? When 2 tangent lines come from the same point, those 2 lines are congruent, right? Same thing here. These two lines come from the same point, so this is congruent to this. These two lines come from the same point, so this is congruent to this. Now, these all might be congruent to each other, but it doesn't give me any measurements here. So, actually it does. It tells me it's a square down here, but let's pretend like it doesn't give me measurements. All I can assume is that these two lines coming from the same point are congruent. This tells me it's a square, so I know all four sides are the same length, and I know all the angles are 90 degrees, so therefore I know all of these little line segments are the same length. Right? Over here, it tells me that this is a hexagon. It's circumscribed around this guy, and all of these lines are tangent. It does not say it's a regular hexagon. We would have to know that all the sides are congruent, right? Because some could be different sizes than others, I guess. Okay, so here's an example of of a circumscribed triangle around a circle that's not a regular triangle, right? All the sides are not equal. So we can see that here. So even though these two sides are equal to each other, these two sides are equal to each other, and get one more. These two sides, are equal to each other. These two, these two, these two, they're not all 6 equal to each other, right? They're not all congruent to each other. So here, both sides are 6. Here, one side is 8, so the other side has to be 8. And here, one side is 12, so the other side has to be 12. Now, if we wanted to find the dimensions of the triangle, the length of all the sides, we would just add those up, right? So this guy is 18, because it's 12 plus 6. This side is 6 plus 8, so it's 14. And this bottom side is 12 plus 8, so it's 20. So that's the length of the triangle. I didn't even read the directions yet. ABC is circumscribed about circle of 0, or circle O. So points D, E, and F are points of tangency. Therefore, AD equals AF. That's what we just marked congruent. These two are congruent. These two are congruent. And these two are congruent to each other. Blah, 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 blah. If we add all 6 sides up, that equals the perimeter, right? This little side plus this little side plus this plus this plus this plus this equals the entire perimeter of the triangle. So we know the perimeter equals 52. Is that what it asked us to find? Oh, find the perimeter. Yeah, 52. We could also add up just each side individually. 18 plus 14 is 32 plus 20 is 52. So we're just adding up all the sides. 12 plus 6 plus 6 plus 8 plus 8 plus 12 equals 52. All right, so let's use what we know to answer some questions down here. For each figure, find x. I'm going to use my red pen. This is 13, so I know this is 13. This is 10, so I know this side is 10. Where is x? Did I miss it? I don't see an x. Oh, this whole thing x. This is x. I didn't realize that. So it's made up of 13 plus 10. This line segment plus this line segment. So 13 plus 10 equals 23. X equals 23. Okay, number 2. We're looking for just this little guy. Okay, it's equal to this little guy. This side down here is equal to this side up here. This line congruent to this line, and this line and this line are congruent to each other. Okay, so we're looking for x. If I know this entire side is 26, and since this is 18, this has to be 18. So 18 plus what equals 26, right? 18 plus 8 equals 26. So this side has to be 8 for 18 plus 8 to equal 26, which means this side has to be 8. So x is equal to 8. 4 more. Number 3, we've got, it looks like a square. Appears to be a square. We've got these points of tangency. This is 16. This side is equal to this side. This side is equal to this side, and this is also 8. So this is 8, this is 8, this is 8, this is 8. So since these are both the same, right, we're gonna assume everything's the same. I didn't really know you could do that, but that's what it's looking like it wants us to do. I don't know. All right, so we'll say this is 8, this is 8, this is 8, this is 8. I guess I know these two are the same, so they're both 8. And these two are the same, so they're both 8. 2x equals 8. So x has to equal 4 here. Oh, I guess it was trying to trick me. I'm trying to figure out how to make these two sides add up to 16, but that doesn't even matter. This and this is the only thing we needed for this problem because we had to solve for x. Haha, I had to talk through that in my head. All right, and then here we have a right triangle. We're looking for this entire side. This is the hypotenuse. So this entire side is 6. Over here, here to here is 6. And then plus it's got this little section. And this little section is the same as this little section, which is 2. So this entire side is 8. Right? So my triangle here is made up of 8, 6, and I don't know. So I'm going to use Pythagorean theorem. 8 squared plus 6 squared equals x squared. 64 plus 36 equals x squared. 100 equals x squared. So x equals 10, or 10 equals x. Number 5. Ooh, this is interesting, right? From here to here, those are each 1. Here to here is 6, so here to here is 6. These two are congruent. This side is 2, so this side has to be 2. So this entire side is made up of 2 and 6. This portion's 2, this portion's 6. X equals 2 plus, oops, I'm already thinking of the answer. 2 plus 6, which equals 8. Okay, and then number 6, last one. Here we have to solve for this x. So we know from here to here is 8. So from here to here also has to be 8. So x plus 2 equals 8. Minus 2 from both sides, x equals 6. Hopefully that's making sense. We kind of covered a lot of little rules here about tangent lines, but go back and watch the video if you didn't catch anything, and if you have questions, please shoot them my way. Thanks.